Okay, in the event that you're having to watch this from home, this is on power. It's actually section 610 of the book. We are skipping around a little bit to make sure that we can get through with all of the content before we go on Christmas break. So this is, again, on power. It's in section 6.10. Quick show of hands. Who had to do any shoveling of snow yesterday because of the snow coming down? Anyone here do that? A few people. You guys shovel it manually, or did you use a snow blower? Manual shoveling? Kian?
Yeah,
manual. Anyone here have a snowblower perhaps in their family that they? Okay, so let me ask you this conceptual question. To move the snow from your driveway takes some work. Whether or not you do that manually like you guys did, having to apply a force or a distance, move the snow from the driveway off to the side, or use a snowblower, in which case is more work done on the snow, do you think? Moving it by hand or using a snowblower? In which case is more work done on the snow?
Snowblower, because the snow gets thrown further.
If that's the case, but let's assume for a moment that the person moving the snow by hand takes it and throws it to the same spot the snowblower would do. So I'm going to try to put some qualifiers on it. So we're going to move the snow from the driveway, and they're going to throw it off to the side, and let's assume, just to make things comparable, that they throw it the same distance away that the snowblower would be. In which case is more work done on the snow? You guys are going to do the same. What's different there, so work again is a transfer of energy. In order for me to move that snow, I'd have to exert a certain amount of force or a certain amount of distance. Whether or not I throw it with the snowblower or I do that manually, the amount of work you do on the snow should essentially be the same because it's about an energy transfer. What's different there is power. Power is simply the rate at which we do work. So if I'm using a snowblower, I'm going to be able to do that work more quickly. When I was a young person, I had to go out and shovel the driveway for my family, and it might take me an hour to do that. It's a fairly long driveway. I had to do all that work manually. When I got older and I got myself a snowblower, I could do that maybe 20 minutes. I can get that work done more quickly. Go ahead. Are you sure? Was there a question about what a snowblower is? No? Okay. Don't be afraid of stopping. All right. A rate at which we do work or the rate at which we transfer energy. Do you guys have a packet? Did you guys get a gray packet? You might want that. Is that what you're asking? Maybe? Would you guys like one of these? Just speak up. I don't want these. All right. When you guys left on Friday was the last day I saw you guys. I don't think I had these things. We hadn't started this unit until after that. So all right. Whether or not you run or walk up the stairs, the work you do is the same. What's different is the power. When you run up the stairs, you're doing that work more quickly. So we would say that running up the stairs is a power kind of activity, whereas walking would be less powerful. Now, we quantify things in a physics class. So power is, again, work. It's a rate at which we do work. So what that would mean is we would take work divided by time. Or in the more general sense, we could say it's energy transferred divided by time. So again, one of them has to do with the concept of work, a force acting through a distance. The other one is just about energy transformation. So work divided by time or energy transformed. Now, we like to simplify things wherever possible. So let's, instead of using work divided by time, let's use a set of symbols for that. So I can say it's work over T, so W over T. Some of you might recognize that work could also be computed by a force times a distance. So for this one, I'm going to write. I could take that work and make it be force times distance and divide that by time. Now I'm going to sort of ignore that cosine of the angle business. So we're going to assume that that force is in the same direction as the displacement. In your math classes, you can do some associative properties. Instead of grouping the force with the distance, I could take that distance and choose to group that with the time. So this is just an associative property of division. I could take that d over t and group them, and I could think of power as force times velocity. So another way that I could do this is I could do a power as force times velocity value. If the force is variable, the best I can do is just do like an average force times the velocity. Sometimes we know how much work we do. Other times we just know how much force we exert multiplied by how fast an object is moving. Let's talk really quick about units. The SI unit for power is the watt. So when you start talking about power, look at units, it's the watt. 1 watt is equivalent to 1 joule of work done per second. So we say 1 watt is 1 joule per second. If you had a snowblower, and it was a gas-driven snowblower, you might look at the rating of that engine, and it wouldn't be measured in watts. What would it be measured in? Not kilowatts. Not for standard motors and stuff in horsepower. So the original power unit that we used was a horsepower. Truly, it actually named based on how much work horses could typically do, the rate at which they could do work. So 1 horsepower is equivalent to 746 watts. So when you start looking at engines and you start talking about your car, how much horsepower does your car have? We typically use horsepower to describe bigger things like engine power, but the SI unit we use is the watt. Okay, off to the right, you have Michael and Jim. Michael and Jim are both lifting the same object, the same distance. Could you go to the right of that on that sheet and just calculate for me how much work each person does and how much power they generate? So just take a moment and see if you can do these quick calcs. Michael and Jim, how much work do they do? How much power? Sorry. Do you agree that Michael and Jim both do the same amount of work? Someone shout out for me how much work Michael and Jim do. 200 joules, thank you. They exert a force of 100 newtons through a distance of 2 meters. They do 200 joules of work. Anyone willing to shout out for me how much power Michael develops? Hours work over time. So for Michael, 200 joules in 1 second, so he does 200 watts. And how about for Jim? 200 joules in 10 seconds, 20 watts. The difference there is how much power they generate. Show of hands, agree or disagree? Most or many athletic competitions are power competitions. Agree or disagree with that statement? Many of them are power competitions. Think about it. Think about the 100 meter or the 200 meter dash. The person that wins, if it's a sprinting event, the person that wins that event has to do a certain amount of work to get them from point A to point B, but the winner is the one that does that work in the least amount of time. Right? So time plays a critical role in a lot of competitions. So it's a lot of people would associate power with strength. You guys see how the picture there sort of makes Michael look like big and strong and stuff like that? Yeah? They're doing the same amount of work. But in reality, it's just how quickly they do it. Okay, so most competitions, athletic competitions anyway, are power kinds of things. All right, let's take a look at at some light bulb stuff. All bulbs convert electrical energy in other forms. Power just measures the rate at which they do that. So when I look at the wattage of a light bulb, we can associate the brightness of that bulb oftentimes with the wattage of it. Besides the process through which light is created, the bulbs that are shown down below differ in life expectancy and something called efficiency. Now, I thought that efficiency was a well understood quantity from just basic life stuff, but it turned out kids in my 5th hour, they're like, I didn't know what efficiency was. So I assume that might be the same for you guys. So I'd like to take a moment. I took the opportunity to get out some light bulbs, and I wanted to show some things related to this efficiency. Come on up for a few minutes, if you would, please. Will you grab the lights for me over there? Come on up. Okay. Now, this demonstration used to be much more much more practical in today's world because all the light bulbs were a certain kind called incandescent. So these bulbs here, ooh, don't stare directly at it. This kind of light bulb is called an incandescent light bulb. There's another one that's incandescent. By the way, I only do this demonstration for my brightest classes. Thank you. I'll be here all week. Do you guys get the plan of works?
We would be your brightest.
Thank you for that. You're right. This one says 75 watts. This is a 75 watt light bulb. This thing's been on for 10 seconds. How much energy went through this thing?
4.
It's a 75 watt light bulb. It's been on for 10 seconds. How much energy has gone through it? 750 joules, because 75 watts means 75 joules per second. So if I did an energy, would you guys agree I could take the energy, power is equal to energy over time, just make that be energy's power times time? 75 watts for 10 seconds is 75 joules per second times 750 joules of energy in 10 seconds. Can you guys tell this is less bright? Can you guys tell that that's less bright? If that's 75, what's this one?
35.
Nice try. It's actually 40. All right, now, if you were light calibrated, you could tell that. But now, don't touch it, but put your hand close to that. And just don't touch it. Can you feel the heat?
Mm-hmm.
Okay, put your hand around that one. Don't touch it. Can you feel the heat?
Yeah.
Yeah, not as much. That one's hotter, right? Mm-hmm. The idea is that these are very inefficient light bulbs. It may be 75 watts of electrical energy, but how much is actually electrical power? How much is actually going into light versus heat? Anyone know what the efficiency is on this?
2% or something.
It's actually a little bit better than that. It's about 3%. Now, what that means for incandescents, about 97% of the energy that goes into heat. The other 3% goes into light. Makes these good for easy bake ovens. You laugh, but a lot of people do that stuff. Right? Raise your hand. You've ever used an easy bake oven? You still do it. Yeah, look at that. When you're a kid, right? But they bake really well because of the heat they're generated. All right. Now, efficiency. How much we get out versus how much we put in. I'm going to try this one here. Now, this is a different kind of technology. Incandescence, it's a really small filament that electrical current flows through, and it gets so hot that it starts to glow. So this is a certain kind of technology. 97% efficient into heat, 3% efficient into light. Now, do you guys notice it took maybe 15, 20 seconds for that thing to get to its full brightness? Brighter, dimmer, or about the same as these? How does it compare in terms of brightness to these things? Don't stare at it, but just get a sample, get a sense of it.
It looks a little bit brighter, although it's starting to turn green the more that I look at it.
Oh my gosh! Don't stare at it.
For my eyes.
All right. Are you ready? Now look, I have it hidden. Are you ready? Okay. Which one's brighter?
That one.
Would you guys agree that? Ouch. Actually, it's not hot. It's weird. It's not hot. This is burned my hand with that. This is not that hot. I know it's crazy. Now, what would you estimate? 75, 40. What would you estimate is the power of that light bulb is brighter?
That's about 15 watts.
It's actually 23 watts. Thank you. It's 23. You might say, wait a minute. 75 and 40. This is only 23 watts. It's about half the power of that one. It's about a third of the power of that. Yet it's actually brighter. What's different there is the efficiency of it. Okay. So how efficient is it? Now, for this last one, you know, most of the bulbs today are not fluorescent. Well, you can't even buy the incandescent. You guys know you can't even buy those anymore.
Really?
You can't buy them. They just, I have a whole stash in these. Oh, I shouldn't tell you this. Because everyone likes the incandescents, but they're very energy inefficient. Say again.
Why do they like those?
Because they give the warm glow. It's like it just feels, it just feels nice.
Maybe you can have
It's
warm
almost like
LEDs
natural
like that
to-
exists.
Well, okay, I'm not sure. It's debatable. Let me try this one. Now they have warm color associated with them, but it's just not the same. Maybe it's just because I'm old.
It's like
But-
a house. It's
Say
like
again?
house versus hospital.
Thank you. Yeah, I'll take that.
Warm light versus
Thank you.
cool light.
This was the original kind of LED bulb. The original kind of LED. It's that big a globe and everything like that. I don't know why I still have this one in there. It's in my cupboard. How many watts would you say this one is? It's about 8 watts. 8 watts. Yeah, so the idea is that as we've gone from these to these, it's because the efficiency is greater. Let's see. And this is 3% efficient. This is about 20% efficient, which means it's about 6 to 7 times as efficient, which means I need 6 to 7 times as less energy to be able to run that. This is about, let's see, if this is 3% efficient, this is about 60% efficient. What that means is that 3 goes, that's 20 times more efficient, which means I would need 20 times less energy if I'm going to use this like no. Okay, it's that idea. Okay. Again, only my brightest classes would I do that with, and you guys all passed. Anyone else see? Just the one. Yeah, sorry. Can you walk safely back to your desk? Don't trip over anything. All right.
I love it when I see purple and green.
Oh. All right, guys, we gotta finish this up really quickly here. I want to do a few problems with you, and I don't have a lot of time, but if you can do work calculations, you can do power. The first picture up there is a picture from a Rocky film. Which Rocky film? 1, 2, 3, 4, 5, 6, 7, 8, 9, could be up to 20. Which Rocky film is that from? 4. That's where Rocky was fighting Ivan Drago in the former Soviet Union. So that's Rocky pulling his brother-in-law, Paulie. All right. How much Rocky pulls this 1,305 Newton sled along a snowy pathway by pulling horizontally on a rope. Rocky pulls with a force of 42.3 newtons. Sled moves 16 meters in 3 seconds. How much work does he do? How much power does he generate? So work again is force times distance. Since he's pulling horizontally, that cosine of theta would be 1. Let's see, which one do I use? The 1305, the 42.3. Do I add them? Do I average them? Which one do I use? I'm not lifting the sled. If I were lifting the sled, I'd use 1305, but I'm pulling the sled, so I'm working against friction there. So I do 42.3 newtons. He pulls at 16 meters, so I just multiply those numbers together, and we get the amount of work he does. 676. Thank you. 676, and then throw some units on that for me, Xavier. Joules. If I want to get power, it's just simply work over time. So he does 676 joules. Get out of there. Don't know how to get on there. Okay, 676 joules. And that took him, 3 seconds? So we just take that division, and we get a certain amount of power. Thank you. 225.
Watts.
What? Did you? What? No, it's 225 units for this.
Watts.
What? There's 225 units. I'm just joking. Thank you. So some people think watt is what? Just joking? Yeah. I know. I got you. I mean, I have to do a little bit of play on words with you guys. All right. Raise your hand. You've ever done any pull-ups? Few people. Person weighs in at 750 newtons. He does some chin-ups. His arms are 62 centimeters in length. That's pretty typical, 62 centimeters. He does 8 chin-ups in 23 seconds. I'd like to know how much power or how much work he does against gravity and then how much power he produces. Try both of those. See if you can do it. I'm going to see if you can follow along with some reasoning for the second part. How much work does he do against gravity? How much power does he produce? Go. Agree does about 3,720 joules of work against gravity. 750 times 0.62, there's 8 of them, so it does that. Now, when I do power, is it okay if I double 3720 when he does this work against gravity? It's okay for me to double that? You see why that when he lowers himself, would you agree that he's doing negative work as he lowers himself? But you can still get strong doing negative work, correct? So in one case, I'm doing positive work. So I'm lifting myself against gravity. I'm doing positive work. When I lower myself, I'm just doing negative work, but I'm still doing work. So why don't we just double that to say that the total work that he does is 3720 times 2, and then I divide that. Power then would be equal to that. divided by, was it 23 seconds? How much power does he generate then? And those that have calculators can do that really quickly. One more time?
23,250 watts.
Ooh, I think it's 23 seconds. So 2 times 3720 divided by 23. I think you're off by that.
323.25.
Okay, 320 was it?
323.25.
Let's just call it 323 watts. Okay? Somewhere calculation problem there. All right. I don't have a whole lot of time, folks, but if you can do power, if you can do work stuff, you can do power stuff. What I'd like to do is just consider, you guys remember how difficult inclined plane stuff was? Okay, so let me take this person that's running up the stairs. And instead of me worrying about dealing with an inclined plane, let me just do a simple calculation and say that the amount of work you do is the same as if you were to just climb a ladder. You don't have to resolve a weight force into a component that's parallel to the inclined plane and perpendicular. The amount of work you do is the same as if you just climbed a ladder. So the idea here is that all I'd have to do is apply an upward force from the hand is the same as the weight. And all I have to do is apply that through a certain distance, where that distance is equal to the height. So instead of having to deal with inclined planes, him running up the stairs and using a fraction of his weight, I can just do the entire weight multiplied by the distance, the height. So how much work does he do? That would be his entire weight, and that distance would be the height. So I just take 65 kilograms, multiply that by 9.8. The height is 18 times 0.14. And that would get me the amount of work he does. And he does about 1,605 joules. If he's doing that in 7.2 seconds, we can get a power. 1,605 divided by 17 or 7.2 means that he's developing power of about 222 watts. Okay, and that's where I'm gonna have to stop it because the bell's about ready to ring. Folks, there's a few problems for you on power. Posted out there for you for today. Obviously, we didn't have school yesterday. Try those, see what you can do. If you could help me with the chairs today, it is Friday, so if you can help me with the chairs, I appreciate it. And you guys have a fantastic weekend. Stay safe on those roads.